Today's background is one that's going to be a little bit popular with the astronomers. It's the Australia Telescope Compact Array, which is out near Narrabri in sort of western New South Wales. Depends how you define western, because if you go almost all the way to the South Australia border, then Narrabri is actually a fair way to the east. It's a radio telescope that has six 22-meter antennas on it. Each of them weighs about 270 tons or so, and they're on this nice long, 3 kilometer long railway track that is kind of interesting because you can sort of look towards the end of the track and you can see that they're actually starting to have to deal with the curvature of the Earth in order to get them in a straight line. I kind of found it really impressive on my trip just because, as an experimental physicist, I like experimental gear, and you can sort of sit there and just appreciate some of the levels of extremes they have to go to in order to get this sort of experiment to work and perform really, really well. So if you're sort of out in Western New South Wales, it's good to have a look at. The town of Narrabri is quite nice as well. Very definitely a good place to stop in for a pub lunch if you're on the road in sort of mid-western New South Wales. So in this second half, what I want to do is talk about a thing in quantum mechanics that we call the expectation value. And it's a really important concept because ultimately it's sort of the bridge for connecting quantum physics back to classical physics. Okay, let's bring up some slides. What the expectation value is essentially it's the weighted average of all the possible measurement outcomes. So if you go back to the first lecture where we were measuring spins, imagine that you can take some spin that's not quite up, and you'll remember there when we measure it, it ends up being up, or sometimes it ends up being down. And when it comes out of that measurement, it ends up in the state that we measure it in. So it's either up or down. But so we can't really take it and remeasure it. But imagine that we had a million of these. We had some sort of magical quantum photocopier that enabled us to make a million quantum spins that are all in exactly the beginning state. What we could do is then put them individually through our Qtron and start to measure up all the statistics for up and down, and we'd find it's a lot of up and a little bit of down and work our way through, right? If we take the average over that very large number of measurements, what we would find is the thing called the expectation value. It's essentially what do we expect it to be after a number of trials. And so to give you a numerical example for this, imagine actually we put in a spin pointing to the right or the left and ask whether it's up or down. What we would get is 50% up and 50% down, as we saw in the last lecture. And so if you take all the plus ones with 50% probability and all the minus ones with 50% probability and add them all together, the answer will be zero, okay? And so the answer zero kind of there says, it points somewhere in between. And if you think about back to classical physics, if you take a spinning football, for example, it's spinning along the z-axis, and you ask what the x component of that angular momentum is, the x component of that angular momentum is zero because the projection of a vector along that orthogonal z direction onto the x-axis is zero, okay? And this is where expectation value is kind of important. What it tends to tell you is what the classical equivalent of a quantum mechanical system is going to do in the long-term average. And this is something that we sort of call in quantum mechanics the correspondence principle. Basically, any system we deal with that has a corresponding sort of physical system in the real world. So, for example, a spinning electron has a spinning football. A particle moving along x with momentum p has an equivalent that's a particle moving along x with momentum p. And what we should find is that the long-term averages of measurements, sort of the weighted average of measurements for a quantum system, will give you an outcome that's equivalent to the equivalent classical system, okay? This is something that you'll see hopefully later in the course called Ehrenfest's theorem, which is usually done for particles with a position x and p, and you basically show that there's, the quantum mechanical version looks like the classical version, and the expectation value is the thing that connects the values together. Okay, so it's quite important. It also tells you basically what to expect for your result from quantum mechanical measurements. And so the way we define this, we often write it for some particular operator as L with angle brackets on both sides. Okay, so there's no straight bracket on either side of this anymore. And you'll see in a minute when I do the algebra for this why you would write it like this. And then we can define it as this expression here. So let's think about what this expression here is for a moment. You'll notice that I'm using lambda. And as we saw in the first half of this lecture, we reserve lambda for eigenvalues, right? I've now got a lambda I, and what that means is there's more than one lambda. And as you'll remember, I mentioned for an n by n matrix, there's up to n different eigenvalues that you can have, right? So for a 2 by 2 matrix, you would expect 2 eigenvalues, which for our quantum spin system will be +1 and -1. What you're doing here is basically taking the sum of the probability of getting that eigenvalue multiplied by the eigenvalue, okay? And so what this is it's the weighted average of the possible measurement outcomes. So the outcome is the eigenvalue, and the weighting is the probability of getting it. It's a weighted average, okay? So it's not just the average of lambda, it's the average of lambda multiplied by its probability of obtaining it. And so if you think, for example, to our case where the spin is along x, and we ask if it's along z or minus z, we would get 0.5 times +1 plus 0.5 times -1 will be 1/2 minus 1/2 equals 0, and the expectation value is 0, which is what you would get. Okay, so I'm going to start from this sort of just definition of what a weighted average of possible measurement outcomes is, and work my way to an alternative expression for this expectation value L, and show you how to get it in a really simple way for bra and ket notation. Okay, so what we have here, let's write down our starting position. It's sum over I, lambda I, p of lambda I, just so that we've got it down on our notes. Okay, so what we can do is we can consider some arbitrary state of the system. Okay, and this is now where we start to use kets like A for arbitrary, okay? You'll remember in one of the past lectures where I had a 2 by 2 matrix, I would have alpha up, up plus alpha down, down, right? So we had kind of our chi as a superposition of up and down. So what we could write here is our arbitrary state is some alpha of a basis state plus an alpha of a basis state, and work our way through. It may not necessarily be a 2 by 2 matrix. And so in a lot of these things where we work through and obtain general expressions here, we know that we may want our quantum mechanics not just to be the 2 by 2 matrix for a simple spin, but it could be bigger, right? If your system only works for one thing, it's not very useful. If your system works for everything, then it's really useful. So what we'll do is we'll generalize this, and we'll say that what we're going to do is make our state to be the sum of a prefactor and all of the possible basis states. And all of the possible basis states are essentially the eigenvectors for the system, right? You'll remember I said that the eigenvalues are connected to the observables as the possible outcomes. And the possible outcomes are what we set our basis by, okay? So what we would be writing here is something that looks like sum over I of alpha I lambda I, okay? And so if it was a 2 by 2 system, this would just be alpha up, up, plus alpha down, down. Okay, just so you can compare back to the earlier parts of the lecture. I'm just generalizing here. Do this quite a lot in physics. All right, so where I'm going to go with this now is pretty much just a voyage of exploration. And this is how a lot of research in physics gets done. Sometimes there's kind of an educated guess to it. You sort of think, oh, maybe it'll be actually useful if I do this thing. Sometimes you just do it from the perspective of, I'm curious about such and such, let me see what it does, okay? So what we're going to do here is we're going to take our operator L, And we're going to let it operate on this arbitrary state A. Okay, and we're just going to work through the algebra for what happens when we do this. Okay, so what we would have, I'll add an extra step compared to my written notes that you'll find just so that we can make one thing clear here. I would have L acting on sum over I, alpha I, lambda I like this. And the one general rule that you saw in the first half that we can carry anywhere is that if you've just got a number, you can take the number all the way out to the front, right? And we usually do that so that we can push operators right up against the things that they operate on, which is the vectors. Okay, so here we could take a alpha I, like in the last, like in the first half, we just took a number lambda and pulled it out the front. Here we can pull the sum of numbers out the front, right? Because you remember we have this idea that if an operator acts on a sum of kets, then it's really just the sum of the operator on each of the individual kets. So what we can do here is write this as lambda I, alpha I, L, lambda I, like so. Okay? Now, the one thing that we know here, and it's implied in the notation, is that the ket here, lambda, is an eigenvector for the operator L. It's why we decided to operate L on it, right? So the operator we're using here is the one that corresponds to the eigenvalue and eigenvector for the state that's the basis for A. Okay, if we put in some other random operator, this wouldn't go anywhere. What we know from the first half is that if we operate L on an eigenvector, what we will get is the corresponding eigenvalue, lambda I, times that eigenvector back, okay? And we will always get the corresponding eigenvalue. So there will be an eigenvalue that corresponds to each eigenvector, and they're almost sort of entangled like a pair, so that if you look at, for example, if you look at up, there will be an eigenvector that eigenvalue that corresponds to it, which is the +1, and it's not the -1 because the -1 is connected to the down, okay? So this is why we're very careful about our I notation down in the bottom. Okay, so what we can do here is basically write this thing as the sum over I of alpha I, lambda I, like so, okay? And then the next step in here is that what we can do is write the corresponding bra for the vector A. So let's write that. So A is going to look like this. What we need to do is take the sum stays as the sum, what it always was. We need to take the conjugate of all the prefactors. So this would now be alpha I star. And then when we go from the ket side to the bra side, everything becomes a bra. And so the lambda I does too. And so what we've got here is lambda I, like this, okay? All right, so what we can do is you can take inner products, right? And when you take an inner product, what you do is you take a bra and you take a ket and you multiply them together. What you also know is that if you use an operator on a vector, then you will get a new vector, okay? So what we're going to do here is we're going to take an inner product. And what we're going to do is take the inner product of the bra A and the new vector, which is L operating on A, right? So this would be L A over here. And the easiest way to put this notation is just to plonk the two together. So what we get here as an inner product is basically something that looks like A, L, A, like this, okay? All right, so let's take what we have from the two equations up above here, number 1 and number 2, for example, and put them into an expression that looks like this. So what we would have is A, L, A is going to be the bra on this side. So this would be sum over, okay, so I'm going to have a little trap in here, which is that the I's that I'm dealing with on this side might not necessarily be the same as the I's that I'm dealing on the ket side. So let's go through and just, for convenience, rename them to j here, just so we can keep track of them, okay? Again, this is one of these things when you're working through problems in physics and you sort of go, oh, hang on, maybe I'm going to walk into a trap here. I should just be careful and I'll clean it up later, okay? So this is now j, alpha j star lambda j. And we can put the right-hand part in here as well, okay? And so we'll keep the I for that. Alpha, sigma I, alpha I, lambda I, ket lambda I, okay? And it doesn't matter whether I switch the bra side to j or whether I switch the ket side to j. So I could interchange those. I'll get the same answer. I could call them k and l, or I could call them a and b. It doesn't really matter what I call them. All that matters at the moment is that I have indices at the bottom, and I want to be able to treat them independently, so I don't go, I, and think that I and I are always necessarily the same, right? I want you to think about this in terms of how you multiply vectors, right? Because when you think about multiplying vectors, you can end up with elements that where one of the elements, say the third one, is pairing off with the second element in the other vector is as part of the multiplication, right? You don't just have first, second, third, which is what you would be implying by keeping them both as I. Okay, so one thing we know is that numbers we can pull out the front. So we're going to pull all the numbers out of the front. And we can pull the sums out too. So let's write this as sum over I, sum over j. Let's pull the lambda I right out the front. Doesn't really matter where you put it. You could put it after. It's the same thing. And then we can pull the two alphas out too. So we'll have alpha j star alpha I. And it doesn't matter which order you jumble the numbers, because you know that numbers multiply in a commutative way. And then what we're going to have here is lambda j and lambda I, okay? All right, so you know that lambda j and lambda I are eigenvectors, and we know that as eigenvectors, we use them as the basis vectors for our system, right? So if you think about your quantum spin, your measurable outcomes are up and down. They become your basis vectors. They're also your eigenvectors. So we know two things here. We know that if we take up and multiply it by up, because we're dealing with an orthonormal basis, and we always do in quantum mechanics, if we take up and up, we will get 1. And if we take two basis vectors that are not the same and multiply them, because they're orthogonal, we get 0, okay? So what we can do here is we can go lambda j lambda I is equal to 0 if I does not equal j, and it's equal to 1 if I is equal to j, right? And so if you think your way through this problem with, lambda I is up and lambda d is down, or the lambda 1 is up and lambda 2 is down, and then work through the possibilities, you'll see that, the way we had an orthonormal basis in an earlier lecture will give you this. Just in terms of notation for later on, this is often a thing that we write as delta ij, with this thing delta ij equals 0 if I doesn't equal j, and it equals 1 if I is equal to j. And this is the thing that we call a Kronecker delta, right? You'll see this turn up again and again in physics. And it's a way of writing this so that you don't have to have two equal signs, 0 and 1. You just go, we have this function delta and it behaves in this particular way. Okay, so we can come back to our line up here. And what we know is that any term where I is not equal to j, this part on the end is going to be 0, and it's going to kill the whole term, right? The only ones that will survive are the ones where I is equal to j. And so the only ones that will survive in this, in the end, is essentially sum over I, alpha I star alpha I lambda I, okay? All the terms in I will be the only ones that remain. I'll let you prove that intermediate step for yourself, that, collapsing the sigma j and sigma I into one sigma I here works. If you just take a small problem in, say, I equals 2, I equals 0, 1, and j equals 0, 1, you can prove for yourself that you only need one sum sign in here and not two, and there's not something that doubles up or undoubles up. I'll let you check that. So then the next step in here is that we know from earlier lectures that this product of alpha I conjugate times alpha I is just the probability of getting that state. So if you remember back to the last lecture where we had the general state chi is equal to alpha up up plus alpha down down, the probability of getting up was alpha up conjugate times alpha up, and the probability of getting down was alpha down conjugate alpha down. And so here, this thing alpha I star alpha I is really just the probability of getting the eigenvalue lambda I. So this is now sum over I p lambda I lambda I. And of course, if we scroll back up to the top, that's the thing that we started with up here, okay? So what we've really shown here is essentially that the way in sort of Bra and Ket notation for getting the expectation value of a particular measured operator that you're interested in is to take your general state. So if we think back to our spin systems, it might be something like chi. And then what we would do in here is put the operator that corresponds to the thing we want to measure. So if we wanted to measure, say, the spin projection along Z, it would be the operator sigma Z that we'll see in the next lecture. I'll show you, we'll build this thing up. Chi on the end here. Okay, so we're asking what the expectation value of the measurement would be for the particular state. And it will end up being, in this particular case, the probability of getting a +1 times +1 plus the probability of getting a -1 times -1, right? It's the weighted average of the possible outcomes that come out of the measurement. And so there's actually, this idea of expectation value, this idea of weighted average of outcomes is really just the same thing as taking the state that you're interested in as a Bra and a Ket and wedging it either side of that operator, and that will get you the expectation value, okay? And often it's implied that we will have that we'll be putting an arbitrary or the state of interest into this, right? All the time in quantum mechanics, we're interested in a system and what its state is, and its state will have some state vector. And if we're interested, then the state vector is obviously the thing we're going to put in there, right? So to save us having to write what is obvious to us, which is that the state vector is going to be on the left and the right, we usually just write this thing in terms of the thing that we're interested in knowing the expectation value for. So usually you would see this written as convenient notation instead, sigma Z, okay? And so if you see just the two angle brackets and not a straight bracket on one side or not a straight bracket on the other, you just see the two angles, what it's telling you is for whatever state you're interested in, this thing is the expectation value of the observable that you're writing down. And basically what you have to do is just perform this operation with the Bra and the Ket and the corresponding matrix operator, okay? And as we saw in the last lecture when we dealt with a projection operator, that operator is a matrix. You have a vector and a vector. I always find it's easier to operate to the right because the multiplication is easy to do, and then you just take the inner product of the two vectors, but you can do it the other way and you'll get the same answer, okay? So this is the concept of expectation value, and I think that's where I'll finish today. And in lecture 5, what we're going to do is take what we built up today in terms of eigenvalues and operators and start applying that back to our quantum spin system. So what we'll do is we'll start building matrix operators that work for quantum spin, and we'll do that by working out what the eigenvalues are, what the eigenvectors are, working backwards to get the matrix, and I'll show you how this all starts fitting together as a solid package. I'll see you next time.